We're RSX from the University of Toronto, and we're back to compete for the third time in the URC. We're back with new partners, ideas, machinery, and a huge and talented team. We're lucky to have access to amazing facilities at U of T, and even an entire dome called the Mars Dome for indoor rover testing. Our focus this year is on robustness, because in the desert, anything that can go wrong will go wrong. We've treated the CDR as a much bigger milestone by using it as a deadline for a completely functional rover. We're glad to say that we've achieved just that. So let's dive right in. Last year we chose an unconventional drive system design that had some difficulty navigating the desert terrain. This year we've chosen a much more conventional rocker bogie system and have instead focused our efforts on making the drive system as robust as possible. We've also put significant emphasis on advanced and experimental manufacturing techniques. For the wheels, we extensively tested a number of off-the-shelf wheels using our custom in-house wheel testing apparatus. Since we weren't satisfied with the performance of several off-the-shelf wheels, we designed and manufactured our own wheels using extremely lightweight carbon fiber, expanding polyurethane, and machined aluminum from Protocase. With the help of our sponsors at a local polyurethane manufacturing facility, Talmolder, we were able to test multiple tread patterns, foam densities, and rigidities in order to choose the most effective design for the wheels of our rover. These wheels are extremely lightweight, absorb a lot of impact force, provide amazing traction, and cover our motors to improve our terrain maneuverability. The linkages for our rocker bogie suspension have also been completely manufactured from carbon fiber, which makes them incredibly strong and robust, and also amazingly lightweight. The geometries of these linkages were carefully chosen based on computer simulations to ensure that the rover would be able to overcome the obstacles that we've faced at the URC in the past. We've also made a lightweight carbon fiber chassis, which has been carefully designed to fit all the electronic components and be modular enough to add and remove components required for the different challenges. The chassis also houses a differential gearbox, which connects the two sides of the rocker bogie suspension system and ensures that the two sides of the rover always maintain contact with the ground. We've designed a brand new robotic arm with 6 degrees of freedom, including a spherical wrist that provides us with an effective workspace suitable for all of the challenges. The degrees of freedom have been carefully chosen to allow us to reach any point on the equipment servicing panel and any point on the ground directly in front of the rover. For the astronaut assistance task, we're employing a shovel system in which the arm can push items onto an actuated shovel. Building on our incredibly successful electrical systems from last year, this year our goal is to design custom boards and build a more modular and robust electrical system. Our main integration board houses our sensor, drive, arm, and power distribution boards. Our communication system plugs directly into this integration board, as does our battery bay. We're using a combination of multiple Arduinos and a Raspberry Pi to control the rover, and have opted for a much more robust hard-case LiPo battery solution consisting of 6 5-amp-hour 4-cell batteries. And we're also using our own CNC mill to etch PCB boards, which we're designing using CAD software. A combination of 3 IP cameras serve as the eyes for the rover, giving us wide-angle HD footage, with one camera even allowing for pan and tilt motion as well. Building also on our very successful software, controls, and communication systems from last year, we have revamped every aspect of these systems for greater robustness. Our communication system operates on 3 bands for redundancy: 2.4 GHz, 900 MHz, and 433 MHz for redundant telemetry, all within regulatory limits. Our ground station is an incredibly exciting and sturdy design, as it is actuated and autonomously tracks the rover based on GPS and heading data, and maintains the most optimal connection with it, allowing us to use a highly directive parabolic antenna on it, and omnidirectional antennas on the rover itself. Our wireless systems are able to operate for over 4 kilometers and up to 20 kilometers line of sight. Our software is written in Python and C, and we've made beautiful graphical user interfaces to display critical information from the rover, such as rover health, GPS location, mission status, and sensor data for the science task. The rover is manually controlled via 1 or more pilots trained to use off-the-shelf joysticks and, in some cases, virtual reality headsets also. Our rover is packed with sensors and experiments. On board, we have methane, hydrogen, and oxygen gas sensors, as well as soil moisture and temperature probes, and a microscope which transmits live images samples to the ground in real time. Our drill provides us with excellent samples within the mass range we expect, and our HD cameras assist with gaining the best possible view of interesting geological features. At the base, we have a combination of a series of chemical experiments and an open-source spectrometer we built on our own. Realizing that sensors alone aren't enough, in April we'll be going on a 2-day-long field trip to a national park to simulate the science mission as closely as we can in an unfamiliar environment. We're at the stage now where we're going to spend the next 3 months making the rover even more robust and practice non-stop to create mission and component specialists so we know exactly how to execute and function when we're on the field. We're super confident, have a lot of people supporting us, and are an incredibly passionate team, so we can't wait to participate in the effort to push the limits of space exploration with our rover at URC 2016.